Hello and welcome to Beamer, folks. I thought before we went into the final assembly of the prototype, I would just revisit the reference and do a dynamic test on the TL431. What I've got here is that device, the TL431, under a little bit of white tack and a thermocouple. I've got a meter here which is measuring the supply current. The mode of operation of the reference IC is with the resistive dropper to the compliance voltage, and that resistor is R4 and it's 1.2K. The current going into the device will be this meter here, and it's 200 milliamps FSD. This meter here is measuring that thermocouple, and at the moment it's a cool 15 degrees C. I'll connect up the supply and we'll see what current is being drawn. There we are. So we've got 2.1 milliamps flowing through here, and the temperature is lifted maybe 15.5 degrees C. The supply voltage at the moment is almost spot on 5 volts DC, and as I said, we're getting 2.1 milliamps current flowing through the TL431. The load I've got is, in fact at the moment I haven't got a load at all. It should have about 66k on the output of the TL431, but I sort of decided to test it without a load at all and just see what current the reference chip is actually taking. So at 5 volts it's drawing 2.1 milliamps. Now if I were to increase this to, let's say, 10 volts, there we are, 10.01 volts. You can see that with the resistive dropper the current has increased now to 6.4 milliamps, and still the temperature is holding at 16 degrees C. There's a little bit of time lag between current increasing in the TL431 and actually the temperature on the thermocouple measuring that increase in temperature. There's a little bit of thermal mass with the metal at the end of the thermocouple, and of course being a plastic chip it takes a little bit of time to work its way through, but at the moment it's 16 degrees C, and I'm pretty sure that if I were to leave this for, let's say, 10 or 15 minutes, which is what I will do at the end of this, we'll see what temperature it climbs to. Right, at the moment I've got 10 volts DC, and I've got 6.4 milliamps being drawn by the reference chip under just a resistive supply dropper from the compliance voltage. I'll now increase this to let's say 20 volts. There you are. That's 20.01 volts. The supply has now gone up to 15 milliamps, and we've now got a slight increase, not much, to 17 degrees. So we've got a 2 degree C lift for 10 volts change. Now finally I'll lift this to 28 volts, and that's probably about as far as I would take this. There you are, 20.01 volts, and we've now gone up to 18 degrees C, and the supply being drawn is 21.8 milliamps, excuse me, nearly 22 milliamps. Now at this stage I won't push the voltage, the compliance voltage, any further than that. At this stage I'll measure the output and see what voltage reference we're actually getting. It should be about 2.5 volts, and my meter is telling me to do something or else it'll go to sleep. There we are. There we go. Okay, now what I'll do is I'll do that measurement of the voltage coming out of the reference chip. I'll just disconnect the, disconnecting the thermocouple, changing the volts through to about 6. Plug in, make sure I plug it into the right terminals. Plug in the meter and take a voltage reading from 0 volts to the output of the now this is the output of the voltage reference, and it is 2.496. 2.496, and I'm going to make a note of that, and that is at 28 volts, and I just put it back to the thermocouple. There you are, and it's up at 20 degrees C. So originally we started off at 15 degrees C, and now it's 20. So for the 28 volts change, we're getting a 5 degrees C change, and the output to the reference is 2.496. What I'm going to do now is leave this for 10 minutes and see what temperature the TL431 has risen to. Okay, so I'm now back again 10 minutes later, and you can see that the temperature for 28 volts has gone up to 22 degrees for a current going into the circuit of 21.8. So the temperature's lifted a little bit. It started off at 15 degrees C, so that's a 8 degree change for 23 volts. Right, so what I'm doing now is I'm going to measure the output of the TL431 and see what sort of change we've got. So pop that onto there. I've got the meter set to 6 volts DC, and what sort of, I'm getting 2.494. 2.4, I'll just make a note of that, 2.494. Okay, so what I'll do now, I'll let this cool down a bit, back to 15 degrees, and we'll see what the reference voltage was then. I should have made a note of it to begin with, but I didn't. So I'll cool it down and see what the reference voltage is, and we'll compare the two. I'm looking at this, I think it's holding fairly stable, even though there's a resistive dropper. Okay, after a further 10 minutes, the temperature is settled back again, but the room must have warmed up very slightly. It's now at 17 degrees C, but nevertheless it's close enough. The compliance voltage is spot on 5 volts. And what I'll do now is I'll check the voltage on the output of the TL431, and let's measure the output voltage and see whether there's any difference at all. Okay, I'm getting 2.488. 2.488. I'm making a note of that. Okay, so what am I getting? I'm getting about what's that? 6 millivolts change between the chip being at 22 degrees C and the temperature of 17 degrees C. So there's a little bit of shift there. I'll now go on to the constant current device and see how we get on there, and see whether there's an improvement or not. If there isn't any significant difference, I might stick with a resistive dropper and do away with the constant current, but we'll see. Well, here we are back again. I've now connected up the constant current source, which is made up by Q15 and Q16, with R11, a 47k, acting as a bias down to 0 volts, and R18, which is 180 ohm, setting a theoretical current at 5 volts of 3.9 milliamps. In actual fact, probably due to tolerances, and this is not an expensive current source, so we can't expect too much from it, but it's delivering 3.3 milliamps for a 180 ohm R18 resistor. Again, there's no load on the output of the TL431, so all we're kind of measuring at the moment 5 volts is the current passing through the TL431, and that's the 3.3 milliamps. The room temperature, or the temperature of the TL431, is at the moment up at 18 degrees C, which is, I believe, to be now room temperature. So what I'll do now is increase the supply voltage and see how we go. I'll increase it to, let's say, 10 volts to begin with. There we are, I'm reading 10.03. The current feeding into the TL431 is now 3.5 milliamps, so it's lifted up by about 0.2 of a milliamp. We're still getting 18 degrees C on the reference chip, and I'll stay with that a moment or two just to see if there's any increase at all. It doesn't look as though there's going to be, and I'll increase the supply to 28 volts again, and then come back after about another 10 minutes and just see how much the temperature has risen to. So I go up now to 15 volts DC compliance voltage. There we are, 15 volts compliance voltage, and excuse me, getting over a bit of a cold, to be honest with you. I'm getting a supply current into the TL431 of 3.7 milliamps now. That's lifted, what, 0.4 of a milliamp from 5 volts, and we're still getting 18 degrees C on the chip, the TL431, and I'll increase it even further. There we are, we're up at 20 volts now. We've now lifted to 3.8 milliamps supplying the reference chip. We've gone up milliamp wise. What have we gone up? We've gone up, it was 3.3, it's now 3.8, so that's 0.5 milliamps. Still holding at 18 degrees C. Right, I've now achieved the 28 volts compliance voltage. The supply current has gone up to 4 milliamps now, so that's a lift of 0.7 milliamps going into the reference chip. A difference between 5 volts and 28 volts DC, and we've still got 18 degrees C. So whilst the resistor, and I'll come back in 10 minutes just to confirm that I'll probably lift to probably 19 degrees C after 10 minutes, but we'll see. I'll go away and leave that now for 10 minutes and see what it's like holding this at 28 volts DC input. Well, you can see after baking this at 28 volts DC on compliance voltage for about 10 or 15 minutes, the TL431 is holding at 18 degrees C. I think I saw it shift to 19 for a moment back there. So it's hardly moved, and the supply current is again fixed at 4 milliamps. It was at 5 volts supply, 3.3 milliamps. So there has been a shift there of 0.7 of a milliamp, but it hasn't affected the TL431 at all. All that remains for me to do is actually check the reference voltage to see how that's behaved. So what I find with this sort of thing, you can never really have enough meters, and I don't think I've quite got enough meters. So let me just go into there and go into the socket there, and there we are. Let's check. We're at 6 volts there again. Let's just check this reference voltage, which is here. Right, I'm getting 2.488. 2.488. Well, here we are, 2.488. It's not changed at all. Absolutely spot on. Same as 5 degrees C, and that's the reason why a constant current is useful. I know that they're not significant changes, but they can affect the output, particularly as this is a semi-precision current sink and source. It does need to be reasonably accurate, and these minor differences do make a difference. Just as a final note, with actually there's 2 points that I'd like to make. One is that using the resistive dropper, not the constant current source, but using the resistive dropper, the value of reference voltage value changed from 2.594 and 2.488 at 15 degrees. So between 15 degrees and 22 degrees there's a difference of 7 degrees. The difference in voltage between cold and effectively hot was 6 millivolts. 6 millivolts divided by 7 equals 0.857. So that's 857 microvolts positive per degree C using the resistor, whereas the constant current 2 transistor configuration produced 0. So naturally one would prefer to use the constant current source driving the TL431 rather than a resistor. Okay, well that's that point. The other point I thought I would do is just see how low the supply voltage will go before the reference voltage deteriorates using the constant current 2 transistor configuration source. Right, so the 2 transistors in question were, regarding the circuit diagram, is Q15 and Q16. Right, so let me reduce the supply voltage. At the moment, we've got 10.14. So what I'm going to do is go down, and we've got an output here from the reference of 2.4991. And we just drop it down until we see that voltage kick. Right, I'm down to 5.2 volts, still nothing, no doing, still not dropping. Down to 4 volts. I'm going to use a fine adjustment on this to see at what point it starts to collapse. Well, there you go. I'm on 3.6 volts supply. This meter keeps on reminding me to wake it up. Keeps wanting to go to sleep. So 3.6, that's quite remarkable. Let's see if I can get a bit lower than that. I'll lift the fine up and drop the coarse. Wow, there we are. We've got still 2.49, and we've got a compliance voltage here of 3.1. Surely it's got to drop any moment now. I'm adjusting the fine downwards, down, down. Oh, there we go. Okay, so it looks as though it's 2.96. Well, let's say at 3 volts. At 3 volts it's still there. So my sync source circuit should operate between a maximum of 30 volts DC down to 3 volts DC. And I think that concludes the reference circuit.
This is Beamer signing out for now.